Okay, so welcome to all of you to today's CMCC webinar. Today we are going to talk about snow mountain and its fate with Manuela Girotto. But before I will give you some short introduction about the CMCC. So we are a leading research center focused on understanding the interaction between climate change and society. And we are a non-profit foundation with a collaboration with many entities around. Oh, no, you are not seeing my screen. Probably. Let's try again. Okay. Sorry. Okay, so as I was mentioning, we are a non-profit foundation with with a large network and collaboration around the globe with different other societies. Then we have as our main mission going from models to solution under different aspects. So advancing the climate research through multidisciplinary analysis, then combining what we have, so the tools that we have, so the climate modeling, the impact assessment with the environmental economics, and supporting the science-driven adaptation and mitigation actions. And to do this, we have many multidisciplinary knowledge, and we need to combine them together, going from the climate modeling to impact modeling and environmental economics. To do so, we have internal structure that is given by these three main research institute, four strategic programs, and different centers. So starting from the institute, we have these three different institutes that try to cover the different topics that we are focusing as CMCC. So the first one is the Institute for Earth System and Prediction, which is leveraging the climate modeling capabilities and turning the scientific knowledge into improved predictive tools. We have the Institute for Climate Resilience that is creating data-driven digital representation of the Earth system components to provide the insight risk assessment and policy support tools for sustainable climate resilient development. Then we have the European Institute of Economics and the Environment that evaluate the sustainable and socially enhancing climate strategies and the interaction between environment, technology, and economy. Then we have four strategic programs which are covering different hot topics. The first one is the integration of the planetary biogeochemical and industrial carbon cycle. So focusing on the modeling of the carbon cycle in order to support a transition to a low emission economy. Then we have the global coast as the new frontier, so focusing on the coastal areas and trying to develop digital twins to explore the interaction between the system and the economic processes. Then predicting socioeconomic outcomes in a changing climate to develop integrated models to support the adaptation policies, and then integrating the artificial intelligence and machine learning within the different modeling chain that we are using at the CMCC. To do so, we have also the support of three main centers. The first one is the High Performance Computing Center, which is one of the most powerful computational facility in Italy and also among Europe, which is all dedicated to the climate change activities studies. Then the Advanced Digital Innovation Center, so it's trying to bridging the cutting edge technology with the critical research for the future, an advanced training and education center to provide education and training and exchange of knowledge with the society. Going back to today's presentation, you are not allowed to activate your audio and video. because it's been deactivated by default. So if you want to have any interaction with the speakers, you have the possibility to intervene by asking your question through the Q&A section. And then at the end of the webinar, of the presentation, I will bring to the speaker the main question that you are raising. So now going back to the presentation, which is about how much snow is in the mountains and what is its fate, by Manuela Girotto. So I leave her the floor and see you later.
Good afternoon, everyone, or morning. Can you see my screen?
Yes, I can.
Perfect. Thank you. So thank you for the introduction, Daniele. And I also want to say, if you don't get to answer your questions, feel free to email me after the today's presentations. But I can get started, and perhaps before getting started, I just wanted to give a very brief background about myself, general research interest, and how I got here to understand the snow. I did my master and bachelor at the University of Studio of Padova, so I'm Italian. And the focus of the work that I did there was mainly driven on the groundwater research, maybe local, regional scale. And then I did my PhD at UCLA, that's in Los Angeles, where I started to investigate snow more on the regional to continental scale. So understanding from satellites and the modeling perspective, can we combine them to get reanalysis of snow so that we can make sense of historical trends of snow. And then after that, about 10 years ago now, I joined the Global Modeling and Assimilation Office at the NASA Goddard Space Flight Center that is located near Washington, D.C., where I got to learn a little bit more about global hydrology, and I got to do a little bit more data assimilation on soil moisture, groundwater at continental and global scale. Since 2019, I became a professor at the University of California, Berkeley. So that's on the west coast of the United States, where I continue to lead some of the research that I had in the background. So today you learn about snow hydrology, but again, the research that we do in our research group also focus on groundwater and the associated hazards, as well as changes of the hydrological cycle due to human-driven processes, and irrigation being the primary one. So the approach that we use, you'll see today in this presentation, is a combination of modeling approaches, satellite approaches, and again, a combination of both through data assimilation. So we'll get started. How much snow is in the mountains? So before actually getting started, I just wanted to provide a little bit of background to why we should care. So the first plot here you see, it's in the world where snow is most dominant contributor to runoff. Again, not surprisingly, you'll see that a lot of these regions corresponds to mountains and the high latitudes. The center map here instead shows where humans are located relatively to the snow runoff, and also where the water is consumed by humans in the last map. So when we mask all of these three components together, we get a mask that in dark blue shows snow areas upstreams of high water needs. So these areas are effectively providing water to 3 billion people downstream. So they do rely on these mountainous regions for their water needs. I also want to point your attention to this acronym for those of you that are not familiar with, snow water equivalent. That's effectively the amount of water that is stored in the snowpack, and that's the variable of interest as a snow hydrologist. So we want to know how much water do we actually get stored in the mountains. So I probably don't have to spend too much time on this slide, but this is also highlighting also the fact that snow is vulnerable, of course, because of climate change. And this vulnerability, as indicated in this map from a couple of years ago, it's driven by both, it can lead to vulnerability both in water resources, but also political and societal hazards. So it's not necessarily just a water vulnerability, but it's also leading to political, again, and social economic hazards. So why is that? Well, again, I probably don't have to spend too much time on this audience, but as an illustration, you'll see on this bottom graphic here, just focusing for a moment on the blue lines, these will be a typical, for example, snow melt time series. So you typically will have a peak on the time series around of the snow melt around, say, spring, late spring, early summer. But then with the climate change, you might expect these snow melt to shift earlier in the season, and of course with a decrease on the amount of snowpack. So leading questions such as how do we get the water that we need, where do we supply the water that we need in the summertime, oftentimes for agricultural purposes, for example. So why is it so difficult to get good estimates of snow? First of all, why do we have still uncertainty? So as an example here, I'm showing three main mountain ranges, Andes, the high mountain Asia, and Western US. And I'm showing estimates of snow water equivalent that you will get running a snow model that is fed with perhaps state-of-the-art atmospheric reanalysis. So some of you might be familiar with ERA5, MERA2, GeoDAS, forcings, and so on. So the key point here is that we do feed these models, snow models, with these reanalysis data set. And then as a result, we get these snow water equivalent estimates. So the first thing that you probably notice is that there is a large variability on these estimates. Since I study in the US, comparatively speaking, these uncertainties, for example, for the Western US is about 4 times the size, the volume of Lake Mead, which is also the largest man-made reservoirs in the United States. So all of this to say that these errors in snow water equivalent estimates do propagate downstreams when you want to make, say, an understanding of water budget, human consumption, vulnerability in the future, or snow droughts, and so on. So going back to the question, why is it so difficult to get estimates of snow in the mountains? Well, you can get a classical approach, and you can go out in the field and take observations. So observations, for example, this is probably the richest area in the world for observations of snow. This is the Western United States. So you see all of the dots are locations where we have either automatic measurements of the snow, so this is called snow tell stations, or manual observations of snow, like the one that I'm taking here, going out in the field and getting samples of the snowpack. So essentially cores that you can weight and understand how much water you have in the snowpack. But you can probably understand that, again, if any of you has been in the mountains, and I hope so, the complicated environment that of the mountains are somewhat leading to areas that cannot be accessed to measure, and also a lot of variability. So a measure that I take in a location could be completely different of a measurement of snow that I take, say, even 5 or 10 meters away from the measurement that I take. So very costly and insufficient resources to actually get good ground observation of that snow quantity. So that's why a lot of the work that we do rely on satellite observation. So first of all, I want to say that a dedicated satellite mission that estimates just snow water equivalent does not yet exist, but the community has done a lot of progress using existing and also developing and designing new satellites that can aim to understand the snow water equivalent. So perhaps the most successful one has been using visible and near-infrared observation. So you can think about, and probably a lot of you have seen maps of snow covered around the world and in the mountains, for example, showing here a map of the Alps for a date in 2018 as derived by MODIS. So these satellites, for example, MODIS, Landsat, Sentinel-2, they do provide daily to bi-weekly observations at sub-kilometer scales of whether you have snow covered on the ground or not. But then if you're paying attention, that's really just telling you the snow cover, not necessarily the amount of snow that you have on the ground. So yes, like it's beneficial to say whether I have snow on the ground or not, but they really care about the amount of snow underneath that snow covered. So if you're lucky enough, especially in the Western United States, we have developed over the past 10 years or so, these LiDAR flights. So they're effectively like, it's an airplane that has in their belly, they have installed these LiDAR instruments. They fly over specific watersheds, say 1 to 4 times a year. Their returns that you get out of these laser LiDAR pulses can tell you something about the snow depth. And one can model the snow density, so then we can retrieve snow water equivalent. Again, these are all great, but it's always available only on selected sites and only the times that we have availability on the flights. More recently, the community has been very active in terms of understanding whether active microwaves, specifically from C-band, perhaps L-band, and also P-band, can be used to understand the snow water equivalent in the mountainous regions. And as an example, I think probably this is maybe the first map that we've seen globally that use a C-band. So the C-band is coming from the Sentinel-1 microwave satellite that can tell us a little bit better in terms of spatial resolution how much snow we have in the mountains. Unfortunately, sometimes the physics around these algorithms are not that clear. So the science community, the snow community, is still developing algorithms to get a good sense of robust estimates of snow. But again, this is probably the first approach, the first way that we get to understand how much snow we have in the mountains, a great spatial resolution, perhaps poor temporal frequency, but that also depends on where you're at. So perhaps every 6 to 30 days repeat observations. So one can say, well, can't we just use models to estimate snow in the mountains? And the answer is yes, we could. But as like any other models, the results that you'll get are really just as good as the inputs and the assumptions that you make into this model. So uncertainties around forcings. And again, I gave the example of the uncertainty ranges for those 3 mountain ranges in the previous slides. So you'll see how the uncertainties can translate into snow water equivalent. So models are good, but they are very far from being perfect. And when we talk about mountainous models, the biggest perhaps elephant in the room that leads to errors in understanding how much snow we have in the mountains is really understanding how much precipitation we have in the mountains. And that's because, as you can imagine, snow in the mountains are a very complicated environment. So there are a lot of microphysical and micrometeorological processes that can go into generating snowfall and the variability of snowfall in the mountains. So a lot of the work that I do, as I mentioned a moment ago in the slides, do rely on the principle of data assimilation. So again, we do recognize that observations, for example, have their benefit when it comes down to observe the phenomena of interest, in my case, snow. We do recognize that models could be useful as well, but we also recognize that both two data streams have errors and uncertainties. So again, the idea of data assimilation is trying to combine the benefit of both data streams, so observations, primarily observation from space, from my research, the models, along with their errors and uncertainties, so then we can provide these optimal estimates of the phenomenon of interest. And in my case, the phenomenon of interest will be snow. So using these concepts, I'll introduce now a little project that I led last year or 2 years ago that was really just aiming to understand, can we use a data simulation framework to use those very high, in a way, spatial resolution observations that we get out of the Sentinel-1 C-band microwave observations to try and better understand or characterize orographic precipitation in the mountains. So again, the biggest errors that can lead to modeling uncertainties when it comes down to snow. And the idea is very simple. So again, I think that not many people can argue against me that snow depth is what these satellites are giving you. We can make an argument that that's directly proportional to snow water equivalent. Again, I think many people could agree with me. And then if you were to look at a little bit closely a very simple mass balance equation, we can think about the evolution of snow over time, just being proportional to whatever comes in, so precipitation, evaporation, and melt. And then in this specific project, we assume precipitation to be the primary source of errors in understanding the evolution of snow. And I multiply that precipitation by an error coefficient called alpha. So in a data simulation sense, what we are trying to do is effectively trying to say, let's guess what this error distribution, this alpha, should look like. And for example, let's just assume that to have a log normal distribution. So just sample like 100, 200s of these values of alpha with a specific distribution. And let's try to see if with a assimilation approach, we can get closer to what this alpha, this error in the precipitation should look like as represented perhaps in this very small schematic in the bottom graphic. So again, the idea is what I call a ground-up approach, where we can try to use the observations that we have on the ground to try and infer the errors in that orographic precipitation. So yet again, the most erroneous amount of inputs that we usually get when we estimate snow from a modeling perspective. So we tested this approach in a small watershed in Trentino Alto Adige. Some of the details of the methods that we use are listed here from a snow model, the streamflow model that we use. The watershed had some independent observations. Today in this presentation, we will see streamflow gauges observations, for example. And we tested the scheme with using 3 perhaps state-of-the-art precipitation approaches that anyone could use. So you might think about ERA 5 as more of a modeling reanalysis type of data set. iMerge, derived from the Global Precipitation Mission, more of a satellite-based precipitation product, and then a classical kriging in situ observation of precipitation. So first of all, notice that they are different in spatial resolution, but also the amount of precipitation is drastically different from these 3 data sets. And then we use a particle bed smoother. So for those of you that are familiar with the data simulation scheme, our ensemble was about 200 member big with a log normal distribution of that error in the precipitation, unbiased and completely 100% error in that error in precipitation. I would like to draw your attention also on for a moment about the topographic features in the watershed. So of course, higher elevation in the outer edge of the domain, and the valley is more of internal. So where the river gauge will be at the outlet here, where my pointer is at. So the first set of results are shown in this slide here. So here I'm showing effectively what the snowfall correction factor looks like after I do my assimilation of the Sentinel-1 snow depth observation. So again, the first thing that you notice is that it's really dependent on the elevation patterns that we've seen in the watersheds. Again, the 3 now panels shows the in situ precipitation, ERA 5, and iMerge. So the panels really are telling you what are the coefficients that will have to multiply these precipitation data sets with in order to get maybe decent estimates or a decent orographic patterns of precipitation for these watersheds. And again, the other thing that you can notice is that these values, green is above 1, red is less than 1. So it tends to increase snowfall for the higher elevation and then decreasing it for the valley. And despite the fact that we only had 4 years to test this analysis, we started seeing that there is some interannual consistency across the years. And that can have perhaps implication if you are a water manager and you're looking into the next year, you can start making a first guess of what the error should look like based on the history of these snowfall correction factors. So again, this is all to say that this type of data simulation approach could be seen also as downscaling method for these coarser precipitation products that we typically use in our snow hydrology modeling, for example. So looking a little bit closer at that snowfall orographic patterns, what I'll show here in this graphic is an accumulation of snowfall for the winter season. So we can imagine winter to be, say, from October 1 to April 1st. So again, if you were just to use the out-of-the-box precipitation products from, say, the in situ, ERA 5, and the iMerge, you'll get just those red dots. that you see here. So you see how with elevation, if you were to draw a line with your eyes across these red lines, you don't really see much of an orographic precipitation effect right there. But then we start seeing it from the results from the data simulation that are indicated by these blue dots. So again, a stronger perhaps increase in orographic precipitation up to 2,500 meters in elevation, and perhaps more of a modest increase for higher elevation. Maybe too cold to actually lead to more enhanced precipitation for this elevation. So again, the key message here is that when we do that data simulation approach, we do tend to get better consistent orographic patterns in the specific watershed. When it comes down to validating this approach, we can look at stream flow, for example, observation. So what I'm showing in this time series is again, 4 years time series of what the stream flow looks like at the gauge in the black dots. And what you will get if you were to use a model only, so without assimilation in the red, and then with the assimilation in the blue. So you can start seeing this is a case for the in situ precipitation, but you can start seeing that you do have better agreement with in situ observations when you look at the blue line, so from the assimilation of the snow depth observation. And this is a little bit more clear when we reproduce this graphic in terms of flow duration curves. And we notice that most of the improvements or the agreements with the observations tend to align with the high flows during summertime. And the hypothesis that we make here is that, well, because we are effectively redistributing snow and putting more snow in the higher elevation, less snow in the valleys, what effectively is doing is that we are readjusting the timing for that water to get down to melt and then get down, trickle down into the outlet. So then we are releasing water via snow melt a little bit more slowly just because we have redistributed through the watersheds. So the first question of my talk was how much water is in the mountains, how much snow is in the mountains. And maybe to answer that first question was that, well, the answer to that question, we're still uncertain how much snow we have in the mountains, but we did make some progress, and that was made through the advent of new satellite approaches and also data simulation techniques. And as an example, I provided that assimilation technique that use one of these probably state-of-the-art satellite observation, like the one from Sentinel-1 that gets snow out of the C-band microwave observations to lead to better understanding of the orographic patterns of precipitation. It's an approach to downscale those precipitation patterns and therefore improve stream flow estimates, especially in those high flows because of the redistribution of snow across the watersheds. So now we can tackle the question, okay, what is the fate then of snow? So one can think about that question in two ways. So one can think about the question of the fate of snow in a climatic sense. So one can say, well, what is the fate of snow, say, at the end of the century? How much snow do we have left at the end of the century, given some climatic predictions of the end of the century? But one can think about this question a little bit more in the shorter time scale. So one can think about, well, on a seasonal basis, once the snow melts, where does it go? Does it end up in the aquifers? Does it end up leading to hydroclimatic hazards regulations, for example, droughts and so on? So we do tackle both questions, but I think today, for the sake of time, I'll probably just look into the climatic sense fate of snow. So if you do have questions, happy to answer after the talk or reach out to me after the seminar offline. So let's start looking into what I mean by looking at the fate of snow in a climatic sense. So again, in order to answer this question, we do rely on CMCC simulations, and I know this CMCC is part of these efforts. So we use, so for those of you that are not familiar, these are climate predictions. The major modeling teams globally came together to provide past, present, and future scenarios of what the climate will look like under specific scenarios. In the next few slides, we present results from the middle of the row scenario, so SSP2, and then a scenario where we increase the fossil fuel development in the future scenarios. And we look at models that only have also the coupling with the lens, so then we can look into snow evolution. So we look at this problem of the fate of snow in a climatic sense by looking at snow drought. And through this index here, this index snow water equivalent index is effectively a index that compares present and future amount of snow water equivalent compared to a reference normal. And the reference normal to us will be the historical period. So then this graphic here shows for the main mountainous regions, shows the distribution of that snow index for historical, present, and the two future scenarios, distributions of that value. So again, not surprisingly, you'll see that it is centered around 0 for the historical scenario and also perhaps for the present time frame. So indicating that the amount of snow or the reduction thereof has not really reduced so far due to climate variability and change. But then no matter what scenario we look into, like either the middle of the road or the SSP 5 fossil fuel development, you'll see that this snow index is reducing. So we are expecting to have more drought in the future, and these droughts will be more frequent. And then if you can look at also the distribution, the bellies tend to be more uncertain, so more all over the place, indicating that these droughts will just be more uncertain, or the amount of snow in the future will just be more uncertain. So we went also ahead and tried to identify what are the causes of these snow droughts. And again, with snow droughts, it's a little bit more complex. It's not difficult, but it's a little bit of a step ahead with just an hydrological drought. When we think about drought, we just think about lack of precipitation. But with snow drought, it can also be that we do have precipitation, we do have the moisture amount, which is just too warm to actually form snowfall and have snowfall that sticks on the ground. So that's why we define warm drought. So effectively a drought that is led by temperature anomalies versus a dry snow drought that is led indeed by lack of moisture. So again, not surprisingly, the characterization of whether it's a warm or a dry drought led to these results that shows indeed that most of the snow droughts in the future will be led by temperature. So they will be driven by temperature rather than a lack of precipitation. So again, some of you might say, well, this is really not surprisingly. We are expecting the climate to warm, so we know that snow is directly linked to temperature, and this is not a surprising fact. And you're right, but then when we look at closer, the story is not that clear. And this is what I mean. We know that with a warmer climate, we do get more extreme events. And this is, for example, this is something that we've started experiencing in our daily life in events that has happened also in Europe recently. But then this is an example from a colleague from 2023 that indicated the number of days with extreme precipitation for 3 different scenarios, for example. So again, we do expect these extreme precipitation events to increase. So what does that mean for snowfall? Well, we do know that when we have increasing temperatures, perhaps the rain to snow line, so the line where we have the transition between rainfall to snowfall, might move up. But does more moisture or more extreme events means that, for example, we might lead to a warmer or maybe warmer storm might lead to more precipitation higher up in the elevation where it's cold enough to actually accumulate those extreme events. So we tried to answer this question. We started tackling this question, using again the CMCC simulations, but the resolution of the CMCC simulations were really not good enough. We're talking about 100 to 200 kilometers spatial resolution. They were not good enough to resolve mountainous regions. So we used downscaled versions of the CMCC simulations, and the downscaled versions were provided by Alex Hall's research group at UCLA in Los Angeles. We looked at downscale simulation at 45, 9, and 3 kilometers. We only had one ensemble member for the 3 kilometer resolution. So we really just focus on the 45 and 9 kilometers. And the results that I'll show in the next couple of slides are really just showing the 9 kilometer downscaled CMCC simulations. So first results is shown here. So how is snow water equivalent declining or changing at the end of the century. So now we are looking at the Sierra Nevada mountains. So this is a region located in the western United States, as indicated in this small little plot. And apologies, I should have put here also a map of the Sierra Nevada region, but it's effectively a region that increases elevation as you go south, and precipitation is primarily coming from this direction. But again, not surprisingly, as we see in this map, we see that as the temperature changes, so per degree of warming, most of the region, this is a mountainous region, is experiencing declining in the snow water equivalent. And the strongest decline happen in the mid elevation when we start mapping this quantity against elevation. But again, we start seeing also some blue areas, and these blue areas do correspond to regions that have the highest elevation. And you can kind of like see it here, over here. For the highest elevation, you start seeing that there are perhaps increases in the snow water equivalent amount. So does it mean that we have indeed more moisture that can accommodate snow? So we went a step ahead and tried to explain if that was indeed the case, using very simple linear regression. So what we did here was trying to regress or to explain the annual end of century snowfall contribution as a function of moisture. And as a function of moisture, as a proxy for moisture, we use the integrated vertical transport, and as a function of temperature, and as a proxy for temperature, we use positive degree days. And then we use a combination of both. So very simple linear regression to tell us what is the, how good are these variables or these metrics to actually explain the variability of the snowfall. And so we use three models, one that is just dependent on moisture, one that is just dependent on temperature, and the combination of both. So again, not surprisingly, when we use both, the results of the model, of the regression model is better. We explain more of the variability on precipitation, but ultimately it's really a delicate balance, I think, between the moisture variability and the temperature. And I think what I think was a little bit surprising and nice to see is that there was also a difference between whether you look at eastern slope or western slope, or better, leeward versus windward side of the slope. So the precipitation is coming in this region from the west. So the water availability indeed was more important in the eastern slope of the Sierra, where we tend to have more of a rain shadow effect. So the water availability in those regions was much more important, whereas temperature was more important in the windward side of the mountains, where temperature is really leading that change between rainfall and snowfall precipitation. So to conclude also this part of the talk, so how much snow will we have at the end of the century? Again, looking into the fate of snow in a climatic sense. Well, again, we might expect more frequent and uncertain distribution of snow droughts, predominantly warm droughts, so driven by temperature rather than lack of precipitation. But again, those high resolution predictions were really able to disentangle a little bit better that balance between moisture availability and temperature, showing that the snow line again is moving upward, but perhaps those higher elevation might accommodate a little bit more snow in future scenarios. So with that, I'd like to thank you for your attention, and also acknowledging students, postdoc, colleagues, and of course, source of fundings that have helped with this research. And I'm happy to take any questions. Thank you.
Thank you very much, Manuela. If you have any question, you can type them in the box below Q&A. And meanwhile, I'll start with a very first question. In your slide, when you're talking about the verification of the improvement, let's say, of the precipitation representation in the Trentino Basin, when you compare with the river runoff, so I think it's like 19 or something like that. Yeah, here. Here, okay. So there is still some differences with the observation dots that we can see. Did you add the possibility to make some evaluation if it is still something related to uncertainties of the observation, or maybe some differences coming from reduced representation of the melting and refreezing processes of
Well,
snow,
yeah.
even or glacier. I don't know if in that specific region there is, but I don't think so. But yeah,
No,
just to
but
see.
again, I think I also want to point back that this was using a very simple snow model.
Okay.
So I think that a lot of the processes, because we were really just trying to target in precipitation. So first order degree, can we improve precipitation and can we have a better understanding of what the snow, the stream flow would look like? So there's definitely a lot of room for improvement here. We didn't really try to resolve all of the different differences that were here. Glacier is, I don't think it's going to be a contributor here in this specific watershed, but it's definitely something that we have some work in progress that will continue in a way this work and extending it more to the entire Alp region that will probably do a little bit of a better job in looking into other source of variability that can lead to these differences. Again, the main scope here was, can we try to fix the first order degree precipitation issue? And the answer was yes. We compare that to the prior, we can do so.
Okay, great. So I'll start to provide some questions from the audience. The first one from Juan. Have you interacted with water managers interested in the future of water in California? How did you deal with the uncertainty when communicating the future scenarios of snow water equivalent?
Haven't done that yet. I haven't really communicated with the water resources in terms of climate change and how we'll expect that to happen. Definitely something that we'll need to do. And again, I'm probably well positioned in our department is called the Environmental Science and Policy Management. So I'm sure that some of my colleagues have started to look into that, but I haven't done that directly. Yeah, there's a lot of uncertainties. And of course, a lot of the data that they still use are those in situ observations that I showed in one slide. And those in situ observations tend to be usually on mid elevation, so they're not very high in elevation. So some of them started going dry. So they are aware that there is, of course, this problem, and then it will just increase in the future. Except that, again, I didn't do that communication myself.
Okay. And then we have a question from Paolo. Have you thought about including machine learning to enhance some aspect of this work? For example, to design a data-driven snow drought index rather than defining it.
Yeah, so I think the machine learning component that I do in my work was not necessarily to define this drought index, but one thing that we did a couple of years ago, we tried to use smart approaches or data-driven approaches to try and come up with a better way that we can estimate snow in the mountains. So what we saw, and this is again going back to the point about the water managers using those in situ observations. So currently they just use these in situ observations and then they try to say, okay, this is representing the snow in a specific domain. So what we tried to do was to come up with a model that better understand the various spatial distribution of those snow-tail sites using more or less complicated data-driven approaches. And what we found was that using more sophisticated data-driven approaches in that sense was leading to improved understanding of the how much snow we had in the mountain. So the direction of data-driven approaching is something that we are tackling currently, but more so in the terms of estimations of the snow water equivalent rather than defining snow drought indexes. So trying effectively to combine all of the various data source that we have. As I mentioned a moment ago, we said we don't have a dedicated mission for snow, but we do have a lot of other missions that can tell us something about snow. So the idea of this data-driven approach is like, what if we combine all of them together? Do they tell us something more than just what we know using physical-based models?
Okay, thank you very much. Then we have the question from Dana. What about the timing of the snow water equivalent? So in some mountain location, the signal are mixed for the fall season. showing both advancing and retreat of the snow onset dates. While during the spring, the change signal is more clear, so showing earlier snow melting.
Yeah, so I didn't really tackle yet that problem about the reduction also or the shift in the fall snow. To be honest, I don't think that that was an issue that we found in the Western United States, where I usually focus on my research, but definitely will try to look into that. The biggest problem is coming to the melt, the summer melt when we come down to seasonal snowpack.
And then Andreas is also asking about the snowfall models and linkage with the long-term changing in the sea level. So there is some relation between the two.
Can you maybe
Ah,
expand that question?
this is the question, sorry.
So
It's
the question is, what is
do the
the...
snowfall models predict long-term changes in sea level?
I do not know that question. Sorry.
Okay. Okay, then we have another couple of questions about how accurately can we predict how much snow will we still have in the mountain on both a shorter, so seasonal, annual, and longer time scale of end of the century? Do you think it will be possible to arrive at prediction with a high enough definition that they become useful to planners and policymakers in the mountain areas?
Yes, I'm hopeful. I think it's possible. I think the work needs to be done more so on the for like yes on the future predictions. But I think we need to understand what we have currently. So trying to improve those models for the mountains. So understanding a little bit better the microphysics of snowfall precipitation, and also combining that with these perhaps advanced and high resolution microwave observation that we get from space to get better accurate maps of snow. So then we can start understanding from the past how is snow variability changing location wise, and then how can we move it forward. So I think it's possible. I think we're still working on doing that. And also going back to the question, there's also about the shorter scale, and I didn't really talk about it in the talk, but how to understand a little bit better on a shorter scale where the snow is going, like linking communities. So I talked about snow hydrology here, but then linking that now again, I'm talking, for example, to aquifers, for example, like how do we go from the snow that melts into the recharge of the aquifer? So I think we are lucky enough now that we have some models and some ways or process-based ways to do the linkage. And we do have observations, say, of both variables. Can we try to better understand how this process works? And again, looking into the past in order to be able to understand what will happen in the future. I think the key is looking at the past, current, in order to get to that future understanding, accurate understanding of what will happen to snow in the future.
Then we have a more technical question about the use of the MODIS snow cover data in this study, and if the availability or the usage of higher resolution dataset, such as the hyperspectral, can improve or help in better understand and
Yeah,
get
so
better results.
the MODIS snow cover data that I use in this project, so I use it extensively perhaps to derive those reanalysis. So what I think was very useful with this high resolution snow cover area observation was telling you something about, again, with the framework of that seasonal snow that has a distinct accumulation and snow melt season. So the snow cover area, what can tell you is in the melt season, can tell you how quick the snow goes from 100% cover to 0% cover. So one can make assumption about the energy budget that goes into melting the snow. So if we know the energy budget and you know the shape of the melt, we can retrieve back how much snow you had at the starting point, the accumulation of snow. So I think the benefit of the snow cover area, at least for the snow reanalysis community, has been really just giving us an idea of how quickly the snow melts on the ground. So I think it's definitely useful for that sense. And also we can use it for evaluation of the model. So in this specific paper that I presented here about the precipitation orographic, we use it also to evaluate our snow-covered model with whatever MODIS or an observation was telling us. So then we could use that as an evaluation as well.
Okay. Then about the parameter alpha that you presented is a question about it could be a function of position, time, elevation, just to improve the capability or understanding the amount of the.
I guess that's one of the point that I was trying to make when I showed the 4 years, and I said we do see some interannual consistencies. Of course, they're not like the same year to year, but at least they can inform a little bit better what the general patterns of precipitation should look like for the mountains. So for someone that needs to make melting predictions, they could have at least a starting point from history of what the alpha parameters should look like, if that makes sense. So it is still indeed a function of space and time, of course, but if we do want to make, again, an assumption that's like this is the average over time, and so you can assume that that could be the starting point for future, if that makes sense.
On the shorter time scale, I think it's this question because it's like related to the interaction with authorities that monitor the snow water equivalent in real time. Is it possible to have through this interaction some forecast abilities on short term, I think?
From this specific
Yeah, there is this interaction with the local authorities that have
yeah
real-time observation can be this type of information useful to
yeah
perform
yeah
forecast.
yeah so that's exactly what I was trying to say, that you could have maybe better understanding of that spatial patterns perhaps of snow.
Uh, about the future satellite mission on the measurement of the
Yeah.
snow water equivalent, there is something that you can add about that, or
Yeah, so
that
I
you know
think
about?
yeah, so there's a lot of exciting work going on, especially I want to say in the L band and the P band. And I would say a lot of it in Europe, Canada, the United States. Unfortunately, we do seem to not um, like climate studies as much anymore. But yeah, so there's a lot of work that is focusing the microwave, the active microwave signal. So some work are looking into using volume scattering principles, so treating the snowpack as a mean that has a lot of little grains, the snow sizes, and looking into how the attenuation of that microwave signal is looking into the snowpack. But I think even more so exciting are studies that are looking into the INSAR. So yeah, they are looking into how changes in phase of the signal are linked to changes in the accumulation or melt of the snowpack. And again, there's a lot of excitement and I think work that has been done, but it's mostly in the longer wavelengths of the microwave range. So we're talking about L band, C band. And I started this Modular project installing a P-band antenna, so using already existing signals that are a military communication signal to see if we can get anything out of that signal from a tower experiment up in the Sierra Nevada. So I'm super excited about also development and seeing where the satellite community is going.
Okay. Now, a final question related to the data assimilation methodology. So you applied the PBS, particle batch smoother. Did you try also other methods? And at the end you were then assimilating directly the snow water equivalent or the snow depth or the
Done that.
snow depth. Okay.
So we were assimilating snow depth. For this particular case, we tried to use particle smoother and particle filters. I think we found the particle-based smoother was a little bit more robust because you didn't have the problem of the ensemble collapsing and having to resample every time we had an assimilation going. And I think we do have a student currently that is trying to look into this also from a sequential perspective using particle filter as well. We went directly with particle filter or smoothers, mainly because we know that our models are non-linear, non-Gaussian. So going, for example, with more classical ensemble common filter was something that we didn't do, mainly because we came with the assumption that particle bed smoother were already probably better at estimating the snow that we were looking at, or that in this case was the errors in the precipitation.
Okay, I think we answered to all the questions that we received so far. I think that Manuela is happy to answer to your question if you want to write to her to have a further discussion and information. And
Thank you.
very much, Manuela, for today's speech. And
Thank you.
time. Thank you.
Thank you. Thank you. Have a good rest of the day.
Thank you.
Bye.
Bye-bye.